Denzler, who is going to speak about efficiency distribution in a quantum Otto engine.
Okay, thanks for the introduction and thanks for having me here. So, like you mentioned, I'm going to talk about the efficiency distribution for quantum Otto engine. So first, our motivation for that. So we know that typically if we have a thermodynamic engine, we define its efficiency as the average of the work it outputs divided by the heat we input. But we know that for small systems, work and heat are stochastic quantities. So obviously, one would be interested in the efficiency if we consider both of these quantities to be fluctuating instead of taking the average. In fact, this has already been studied classically by Verli, Esposito, and others, 2014, for a classical engine. And what they found here is like they have the large deviation function over the efficiency, and they found that they can not only reach efficiencies larger than 1 or smaller than 0, but also that the least likely efficiency is the Carnot efficiency, shown here in blue. So obviously we asked ourselves, well, how does it look like in the quantum case? So a short introduction again to the quantum Otto engine. So an Otto engine typically consists of 2 isochores, a hot one and a cold one, where we couple the system to a heat bath, and heat is exchanged, as well as a compression and an expansion step in which the work is performed. The isochores are implemented by recoupling and hence using Lindblad master equations, and the adiabats are implemented by changing the Hamiltonian and a unitary solution. So what is our strategy? Our strategy is we have like the 4 steps of our Otto cycle, and we want to perform a projective energy measurement at the beginning and in the end of all of these 4 steps. If we do this, we are then able to obtain the fluctuations of the total work and the input heat. We first start with the work performed during the expansion step. The work during the expansion step can be calculated, the fluctuation of the work during the expansion step can be calculated quite easily by just applying the usual 2-point measurement scheme, measuring at the point A at the beginning of the step, and measuring at the point B at the end of the step. The initial distribution here is given by a thermal distribution at the inverse temperature of the cold heat bath, and the final transition probabilities are just given by the unitary revolution of the system. One may then also proceed in a similar fashion to obtain an expression for the work during the compression step. For the heat, it's very similar. One has to only take one thing into account. So we still perform like a 2-point measurement. However, we have to know, like obviously it depends on the amount of work that was performed before during the expansion step. We include this by changing the initial distribution here to agree with the final step of the expansion step. So we can see here we end up in a state M after the measurement here. And obviously it has to agree with the initial step for the heat distribution. We also make one further simplification. We assume full thermalization of the system with the heat bath. So the transition probabilities are just given by like the thermal distribution. If we combine all of that, we then obtain an expression for all of the fluctuations, and one can then integrate over all the values of the work and the input heat using the property of the delta function to obtain an expression for the efficiency distribution of our Otto engine. We can see like it's a very nice expression. We can use it very easily. We didn't specify any details about our quantum system, and the only point where the details of our quantum system enter are actually the unitaries during expansion and compression. So we then studied this expression, which is true for an arbitrary quantum Otto system, for the example of a 2-state system in a rotating magnetic field. Why did we choose that? Well, first of all, because like we've seen last week, it can be implemented very easily in an NMR setup, as has been done by Roberto Serra's group in 2018, for example. So what do? We have a system with a magnetic field and the XY plane, and we rotate it at a time 0 from the X towards the Y axis. We furthermore increase the strength of the magnetic field from a value gamma 1 to gamma 2, and thus widening the band gap. For the compression step, we can just inverse the Hamiltonian, and then we get just close the band gap again and rotate the system back to the initial state. We furthermore introduced this one factor here, which was not present in Serra's original work, because then it actually becomes analytically solvable. So if we use all of our expression and plug this in, we obtain this expression for the efficiency distribution. The exact shape is not that important. The only thing that matters here are actually those factors U and V, which give us like a feeling for the degree of adiabaticity of the compression and expansion step. By which I mean If this U takes a value of 1, there will be no energy transitions during expansion compression. If it takes a value of 0, there will always be transitions during expansion compression. We then used this expression and plotted it for 2 cases. The case, as I've mentioned, when U is 1, so there are no energy transitions, and the non-adiabatic step. So we see the efficiency distribution here, and we can obviously see it's discrete because we have a two-state system, so obviously there's only a finite amount of values the efficiency can take. What is interesting here, we see that 3 of those 5 peaks are actually larger than the typical thermal distribution, which is the one when you just divide the average work by the average heat. The most interesting one here is actually one at infinity, which corresponds to the situation when no heat is exchanged, but still a finite amount of work is performed. And this is a very clear feature of the discreteness of our system. We discovered furthermore that those peaks, especially the one at infinity, they disappear just for adiabatic driving. Because we have a peak at infinity, we are obviously unable to evaluate the moments of this distribution for anything apart for adiabatic driving, which is what we then did. And we first looked at the mean efficiency. So we looked at different driving times, tau, and the mean efficiency. So here in blue, we have the typical thermal distribution, average divided by average. And we can see that at the adiabatic step, which maximizes the efficiency for this kind of distribution, our mean efficiency, which we obtain when we directly evaluate our distribution, is much, much lower. It's always lower than the one we obtain when we directly evaluate the efficiencies, the means of the heat and the work. Why is that? Well, the reason for this are correlations between the heat and the efficiency, and hence also the work and the heat in our system. We can see that the correlations are always strictly positive for different temperatures. And we can further see that we use the property of the covariance. We can rewrite actually our efficiency, the mean efficiency with our approach. We can compare it with our approach with the one with the thermal approach. And we can see that the thermal one, our approach will always be lower than the other one because of said correlations. We see also that this term here, shown here, actually it gets lower if we increase the temperature. So the more we go towards the classical limit, the close more and more our 2 values agree, but they will never completely agree. In the end, we also studied the variance and the mean for different temperatures, and we can see a clear transition from the high temperature case of classical systems, as far as we can talk about a classical system for a 2-state system, to the quantum regime for low temperatures. The same holds true for the efficiencies. So I think I was a little bit too fast. So the main ideas, main conclusions of my work are we derived this expression for the efficiency distribution for Quadrant-Otto cycle. For an arbitrary quantum system, one just needs to know the unitaries. And we discovered that the mean efficiency we obtain by evaluating this expression will always be lower for the adiabatic case than the thermal distribution because of correlation between heat and work. Thank you.
So thank you. Questions? So it's early. People are tired from the long week. Yeah. So